Welcome back. Today we're going to look at, in section 2.3, another operation that we can do on polynomials, and that's dividing polynomials. Specifically, we're going to look at two different methods that we can use in dividing polynomials. Of course, we've seen division of polynomials when it comes to factoring and then possibly canceling within a fractional scenario, binomials and such. But we've never really looked at how to do a long division. And so this is going to mirror a lot of the steps and procedures we use in actually carrying out regular long division. Only we're doing this with polynomials. So when we talk about a factor of a polynomial, so we're going to use some symbolism here to just kind of give some general rules. So a polynomial, dx, is a factor of a larger polynomial, f of x. Remember that, in a multi-termed polynomial, whether it has 4 terms, 5 terms, what have you, that anything that would be a factor of that polynomial is something that would multiply into it or would multiply with something else to give us that larger polynomial. So for example, x squared minus 2x plus 1 factors down to x minus 1 times x minus 1. So x minus 1 is a factor of this larger 3-term polynomial. In fact, it's a factor twice. We would write that as x minus 1 squared, meaning it is a second multiple of the larger polynomial that we have there. So when we talk about this d of x, it's representing the smaller polynomial, which multiplies with something else, making it a factor, to give us the larger polynomial f of x. If there's another polynomial q of x, so that when I take f d of x and I multiply by this other factor, this other polynomial which is a factor, I get f of x. So you can kind of think of the example that we have over here, but the notation we're using could work for any size polynomial. If this is a 2-term polynomial and this is a 3-termed trinomial, they would multiply to give me this larger polynomial here. So it doesn't have to be 2 small polynomials like we would normally think. It could be a 2nd or 3rd degree polynomial that's part of or is a factor of a larger polynomial. Now, as you know, sometimes when we do divisions, they don't necessarily go in evenly, right? So I can take numbers into larger numbers that don't go in evenly. There's some remainders left over, but that division can still take place. When we're talking about numbers, for example, if I take something like 25 and I divide that by 6, that 6 will go into 25 4 times, but then we have a remainder left over. And so that remainder is 1. 6 times 4 is 24. So we have a remainder of 1 out of the 6 we were dividing by. This, in fact, is an addition that we would express. 4 and a 6, the mixed number, is really just a shorter way of us writing 4 plus 1 out of 6 remaining. So there's a couple of ways that we can show this. If it goes in evenly, we say it's a factor, right? It is a multiple of the larger. It multiplies to give me evenly a larger polynomial. But if it doesn't go in evenly, we're just doing a division, and it's going to take one of 2 forms. So f of x being our larger polynomial here, if f of x divided by, let's take this one up here, d of x, so divided by some polynomial as well, and I'm putting these here. I don't want you to think I'm making them negative, but So we have f of x divided by, let me use my pointer, divided by d of x equals some sort of q of x. And then they have this r of x here, and I want you to think of that as the remainder, as a reason why they used r. So we got a polynomial from the division, but then there's a little bit left remaining. And so we would express that as this plus my r of x out of, and notice how this is d of x. This is just like what I did here with the numbers. I had 25, I divided it by 6, and that resulted in, it goes in 4 times evenly, but we have this 1 left over out of the 6 that we, the divisor that we started out with. Another way to think of this is that the overall function polynomial is equal to the d of x, which was what I was dividing by, multiplied by the q of x. Notice that this division resulted in this, so the opposite of that, that result times the division plus the remainder gives me what I started out with. We can express that or compare that to like real numbers as well. 25 is equal to 6 times 4 plus 1, right? I have the divisor, I have the quotient, the result of that, plus the remainder. So this is another way of writing that relationship. But of course, this is more theoretical. We're dealing with polynomials, but it's helpful for us to see how this relates to something that we can really grasp, right? You can really go, yeah, 6 times 4 is 24 plus 1 is 25. Yeah, duh, I see that. But a little more abstract here when we're talking about polynomials, but same principles. And a lot of, like just as a general observation, when you're studying math and learning these more seemingly complicated theorems that we've got wording and definitions and small print, right? Disclaimers off to the side where, well, x can't equal 0 and that kind of stuff. All we're doing is trying to generalize the same things that we do with numbers, right? But we're generalizing it with variables so we can apply it in a lot of different situations. So literally these two statements that we have here apply for every polynomial situation. And the polynomials, all they are is expressions of numbers. With variables mixed with numbers and sums and differences, etc. So that's just a general thing to look for those patterns, and it really helps to kind of relate it back to numbers. And then it's not so mysterious. It's not so just something that you would read over and not actually try to think about for a minute or understand. The last part here says either r of x is the zero-part polynomial, meaning just the number with a 0 degree, or just the degree of r of x is going to be less than the degree of d of x here. So this has to be a proper fraction. In other words, we can't have this being a second degree over a first degree, because then this would be able to go into it one more time. So either this is a number, or which has no variable, right? So a constant, no variable, meaning x to the 0 power, so a 0 degree, or it's just 1 degree less than, or just a lesser degree than what we have here in d of x. Doesn't have to be 1 less than, just a lesser degree. Let's really get down and dirty here, and let's go ahead and do a long division. It's a little bit different than, and I'm going to take you slowly, and we're going to do a couple of examples with this, and then we're going to look at another method of doing this. So, first of all, let's talk about what's being divided by what. First of all, the parts that are being divided, we call that the dividend. So, since we're taking this and we are dividing it by this is the dividend, and it's being divided by the divisor. Think of it like a razor, divider, I don't know. That's what's doing the cutting. So we have what we want to divide up. We have what's dividing it, or what we're dividing it by. And then the result is always called our quotient. Okay? And that's what we're after here. So we set this up just like we would in long division. I'm going to put 3x to the third. And we want to make sure that this is in descending order. So 3x to the third plus 4x squared plus x plus 7. Notice that my degrees are going from 3, 2, 1, and then 0. My divisor is the x squared plus 1. Notice that I'm missing an x term. We need to put that in there. So I'm going to put 0x in any spots in my divisor or my dividend where I have a missing portion. And I'm moving it down there a little bit so that we have more room. I didn't give myself a whole lot of room there. So, all right, what is our first step? So our main focus when we're doing the divisors and we're doing the division here is the first terms, right? So that's one thing. Doing this is not terribly difficult in terms of the math that you're actually doing. It's in keeping yourself organized as you're doing it. That's the tough part. And just memorizing, learning, practicing the process. So I look at x squared and I look at 3x to the third. And I say, okay, x squared times what would give me 3x to the third? The other way you could think of it is 3x to the third divided by x squared. What would that leave me with? I'm just going to go over here to the side and just remind us of some of the things that happen. 3x to the third divided by x squared. The 2x's would cancel with these 2x's, leaving me with 1x and the 3. So 3x. We see 3x is what I would multiply x squared by in order to get 3x to the third. So this is the next important thing. I actually don't put that result above the 3x. I put it above the column of numbers that are of the same degree. So since x is to the first degree, 3x is also to the first degree, that's where I want to place the result of that division. So again, I focused on the first terms, and I said, what do I have to multiply x squared by in order to get this? The other way to think of it is this divided by that leaves me with what? And then I put the result over here above the same degreed term. Great. Now we need to figure out what's left over. So I'm going to take 3 and I'm going to multiply it by each one of these here and then put the results in the proper columns underneath the radical. Or it's not really a radical, sorry, the division marker part. So 3x times 1, well, that's 3x. So I'm going to put 3x here. And then 3x times 0x, well, that's just 0. Anything times 0 is 0. And then 3x times 3x squared gives me 3x to the third. Now, as you guys know, we would now go through and subtract, right? If you remember back to how we did this in elementary school or whenever it was the last time you did long division, if you remember it, the next thing is that we subtract. Now, the problem that we have here is we're subtracting 3 different terms, and I want to subtract each one of them. So instead of subtracting, I'm going to put plus negative, and I'm going to change the signs of each of these terms. So I'm going to make that negative 3x squared, negative 0, but that, of course, isn't going to mean anything. Then minus 3x. Reason why is it's a lot easier to think in terms when you're dealing, as you guys know, with integers, positive and negative whole numbers. It's much easier to think in terms of addition. So I'm going to add. So x plus negative 3x is negative 2x. And then 4x plus 0, well, that's just 4x squared. And then 3x to the third plus negative 3x to the third, that's 0. And of course, this is what we always want to have here. And I shouldn't write it with thing. I'm just going to put 0. I'm just going to leave it blank, actually. This is what we want. We want to populate the other two, and we want this to be 0. If this isn't 0, then we have the wrong quotient, or we have the wrong answer up here. Part of the quotient, not the full quotient. But all right, you understand. Now we bring down the next part, which is the positive 7. And we start over again. Again, I'm going to focus on the first terms of x squared, and I have 4x squared. And so we say x squared times what gives me 4x squared. I've got the x squareds, I just need the 4. So add 4 here. And now we're going to go through and do the same thing. 4 times 1 gives me 4. 4 times 0x, well, that gives me 0. 4 times x squared, that's 4x squared. We're going to add the opposite, so I'm going to go through, change the signs. Notice that none of them were negative, so I haven't had to do that yet. Do my subtractions by adding. Really, we're adding these. So 4 plus negative 4 is 3, and negative 2x plus 0 is negative 2x. So we got positive 3 and negative 2x. That's as far as I can go. Notice that I came to the end here of my line. There's no more numbers to bring down. That kind of that's the end of the line. You can't go any further. In fact, I can't take x squared and get any sort of whole number solution without using fractions, get negative 2x. So this part is my remainder. And so as a result, I'm going to write this as plus that 2x plus 3, and it was negative 2x. I'm going to make sure I don't forget that. And put that over my divisor over here, x squared plus 1. I'm not going to put the 0x because that was just kind of a placeholder. But here is my remainder and my resulting quotient. So 3x to the third plus 4x squared plus x plus 7 is equal to, well, or we could put divided by, I'm going to put both here, but equal to 3x plus 4 times, actually I wanted to do that in a different order. That's okay. Just so we have those. So our result, or the product, x squared plus 1, right? That's my divisor there. Multiplied by 3x plus 4, this was my quotient, plus negative 2x plus 3 over x squared plus 1. The other way to write this is to take my dividend, 3x to the third plus 4x squared plus x plus 7, and then that divided by x squared plus 1 will equal 3x plus 4 plus negative 2x plus 3 over x squared plus 1. And looking what I have here, I'm actually going to go back and adjust this a little bit because the first one, I'm just going to leave it as plus the remainder. I don't need to put it over the quotient because that's over here. Oops, I didn't mean to erase all that. But if we were to divide both sides by x plus 1, it would cancel out here, would end up over here. And actually what you would see is the result here. Divided both sides by x squared plus 1, it cancels this part out, leaving me with this. And since it doesn't go into that part, it would be here. So it's equal to the two products plus the remainder. We just leave the remainder as, by itself. So let's do another long division problem here. We're going to take this polynomial, which is a fourth degree polynomial, and we're going to divide it by a first degree polynomial using long division. So the setup to this, always important to keep in mind what is getting divided by and what is going into. This first part will be our dividend. The second one is our divisor. So we're going to take x plus 2 and we're going to divide it into 2x to the fourth plus x cubed minus 16x squared. Notice I'm missing an x term, so I'm going to put plus 0x and then plus 18. I'm going to go ahead and move this down a little bit just to give me a little more room. And then let's go through the process. So I focus on the first terms. I think about x and 2x to the fourth. And I either ask myself, x times what will give me 2x to the fourth? Well, I'm missing a 2, and then I'm missing 3 x's because I want 4 x's being multiplied, right? So I need to multiply by 3 more x's to get that. You can also look at it as a division. 2x to the fourth divided by x, and we see this would cancel, leaving me with 2x cubed. That's what I have to multiply it by in order to get, that's what I have to multiply x by in order to get 2x to the fourth. So 2x to the third is the result that I need there, and I'm going to put it above the x cubed column there so that it's above the same degree term. And now we multiply. We go 2x cubed times 2, which is 4x cubed, and 2x to the third times x, so 2x to the fourth. So now I'm going to subtract, right? But subtracting, these are both positive. I didn't put the positive there, but you could. You could definitely, just bring down this plus, and this is a positive as well. But I want to subtract. So instead of thinking subtraction, though, I'm going to add the opposite. So plus, negative, make them the opposite sign. And then we think addition straight down. Positive 1, x to the third plus negative 4, x to the third leaves me with negative 3, x to the third. And here I get 0. And we go ahead and bring down the next thing, which is a minus 16x squared. If there's a minus there, you've got to bring down that minus with it. Otherwise, when you look at it, you're going to assume it's positive. And again, we focus on the first term. X times what will give me negative 3x to the third? Well, I will need a minus 3. And I've got 1x, and I need 2 more x's, which we expect in this case. And it's in the correct column, the x squared column here. And notice how if you go down, all of these are x cubes, right? We got them nice and ordered. Part of doing this is just keeping yourself organized. All right, and now we multiply negative 3x squared. Negative 3x squared times 2 gives me negative 6x squared. And negative 3x squared times x gives me negative 3x cubed. These should end up the same, right, until we add the opposite. Then they become the opposite. So plus, that becomes positive. So we have a negative 3 and a positive 3x cubed. And this also becomes positive. And we add straight down. Negative 16x squared plus 6x squared gives me negative 10x squared. Bring down the next number here, 0x. And now we, again, focus on the first parts here. X going into negative 10x squared. Well, we need a negative 10 and an x, negative 10x. And that matches up with the column I'm in because I put this 0x here. See how that's important? Let's go ahead and multiply. Negative 10 times 2. Negative 10x times 2 is negative 20x. And negative 10x times x is negative 10x squared. Let's add the opposite. Plus, plus, plus. Add straight down. We get 20x. And we bring down our last number here, which is a 18. Focusing on the first parts, x times what gives me 20x? Well, that's just going to be plus 20. And as I multiply 20 times 2, that's 40, and that's positive 40. And then 20 times x, that's 20x. Let's add the opposite and see what we get with that. 18 plus negative 40 is going to leave me with negative 22, and this becomes 0. So this is my remainder. So we can say plus 22 over x plus 2, and that is my answer for this division. Now we're going to look at another process which simplifies the overall process here. Much simpler than, say, doing long division, because there's just fewer. It's easier to stay organized, and it's not going to take up half your page of paper. So we first want to just reiterate the idea here that we're dividing a polynomial, right? So we're going to call that f of x our polynomial function, and we're dividing it by another polynomial. I'm going to write that as x minus a. The x minus a, if you notice that in this x minus a, we're representing one of the possible factors, if we had a remainder of 0, that's going into the larger polynomial. And so the a value there, if we're thinking about the 0, what would make this equal to 0 is an a, right? And now I know a lot of times we're not going to get 0 as a remainder, but that's okay. We're still doing a division, and we're just ending up with the remainder. So in other words, if I have x plus 2, which is what I have here, with the x minus a, we would want to think of a as being not 2, but negative 2, because x minus negative 2 is what gives me x plus 2. If I have to, and we have the general formula here, shows a subtraction. Remember, whenever we have a subtraction in front of a variable, the variable's value, you want to kind of think in terms of opposite from what you're seeing. And so here, the a value would be negative 2. And that's important because that's what we want to put in synthetic division here, is the a. We want to put a here. Okay. And then I'm going to take the coefficients of all the other, the dividend here. I've got a 2 in front of the x, of course, that's the highest. And then we have a 1 in front, it's a positive 1 in front of x cubed. Then I have a negative 16 in front of x squared. And then I don't have an x to the 1. So I'm going to put a 0 there as a placeholder for that term. And then we have 18. Leave a little space here. And the first thing that we bring down is the 2. Our starting point, we're going to bring that down. And in fact, for what we do with this, we're going to take that, we're going to multiply it by my divisor there, negative 2. So 2 times negative 2 is negative 4. And so I put that right below the next number. Excuse me. And then we're going to add straight down. So addition. Great. We love that. 1 plus negative 4 is negative 3. I also will multiply this by the divisor negative 2. And that gives me positive 6. Negative 3 times negative 2 is positive 6. Add straight down, that gives me a 10. 10 times negative 2 is negative 20, so we put that in the next column there. And we add straight down, that gives me negative 20 here. And then negative 20 times negative 2 is 40. Add straight down, that gives me 58. So, this is the result of my synthetic division here. And this was a 4th degree equation. We're dividing it by a 1st degree equation. And so the new, I guess you would say, first term here is going to have that coefficient, but it's going to have x to the degree that's one less than, what I did there. So x to the fourth. So this is going to be an x to the third. Next, minus 3x squared plus 10x minus 20. That's 20x to the 0, so no x term. This 58 is my remainder, 58 over x plus 2. And this is the result. You'll notice that this is the same answer that we had on the previous slide. 2x cubed minus 3x plus 10 minus 20 plus 58 over x minus 2. Exact same result, but you can see it's a lot sort of less messy for us to deal with. Now, one of the downsides about synthetic division, why we can't just use this every time, and why we need other methods, is that we have to divide it by an x minus a factor. So it has to be a first-degree factor that we're using in this division. Otherwise, the process doesn't work. You'll notice that's what I did on the previous one. We divided by x plus 2, but the first time I did the long division, we actually divided by a second-degree binomial. Normally, a second degree would probably give us a trinomial, but in cases like this, I would have to use the long division method. So it's important to know both, but when we're just dividing by a binomial, x minus a, this is a option that we have for our long division. Let's go ahead and do one more while we're doing this. So I'm going to take my dividend there, 2x to the third. So I have a 2, I have a minus 7, that's my x squared. I don't have an x term, so I'm going to put a 0 there. And then 5 is my 0 degree term. So third, second, first, and 0. I just want to make sure I didn't miss anything. And then my a value here with x minus 3 is 3. Again, think about what you would put in for x to get 0. That's what you want your a value to be here in your little box. Leave some space and bring down the first number, 2. And then we multiply 2 by the number there, 3. Again, this is a process that you just have to memorize. Oops, sorry. I didn't memorize it very well because I did the wrong thing. I'm going to multiply by 3, so multiply by my divisor, that gives me 6. And 6 plus negative 7 is negative 1. And now we do another multiplication. 3 times negative 1 is negative 3. Again, add straight down, that gives me negative 3. Excuse me. And then negative 3 times 3 is negative 9. And add straight down, 5 plus negative 9 is negative 6. Okay, great. So I did my thing. I've divided a third degree by a first degree, so I should get a second degree polynomial here. 2x squared, one less than what I started with, minus 1x, minus 3, that's my 0 degree term, and then plus negative 6 over x minus 3. That is the resulting quotient. Let's look at the one major theorem we're going to look at in this section, which is the factor theorem. And it says the following: a polynomial f of x. So we saw, the polynomials that we were dividing there. And so we're representing that with a function notation, but the function is equal to the polynomial. So the polynomial f of x has x minus a as a factor. And here's an interesting thing that I want to talk about here. If and only if. When we say if and only if, that means this goes both ways. It's not like we're just emphasizing the if part, right? And saying if and only if, as like just emphasis in an argument or something. Specifically, when we say if and only if, that means this also goes in the other direction. So we can say a polynomial f of x has this as a factor if that a value, when plugged into the function, gives us 0. Okay? But then we can also say, because it says if and only if, that if f of a is equal to 0, so in other words, if I plug a into my function and I get 0 as a result, so meaning a is a 0 of that function, then x minus a will be a factor of f of x. So this function, or which is represented with a polynomial, has this as a factor if the value of a, when plugged into the function, gives me 0. And then I can also say if the value of a, when plugged into the function, gives me 0, then I know that a value is a factor of the polynomial f of x. Okay? So whenever you see that if and only if, that means that it goes in both directions. So just kind of playing that theorem out, we start off with this statement that says, given that 2 is a 0 of the function, so in other words, if I were to plug in 2 into this function, I should get 0. We can check that out. They gave it to us, so it's kind of just a matter of trusting them. But again, plugging 2 into there, finding the f of 2, that's 3 times 2 squared plus 2 times, or it's to the, this should be to the third. Something's off here with their slide. I found this a few times. That should be a third. So that's to the third power plus 2 x squared, so 2 times 2 squared, minus 19 times 2 plus 6. Okay, well, let's see if we simplify this out, if it really works out. 2 cubed is 8. 8 times 3 is 24. So we have 24 plus 2 times 2 is 4. 4 times 2 is 8. So that's 24 plus 8. 19 times 2 is 38. And then we have plus 6. All right, well, 24 plus 8 is 32. 32 minus 38 is negative 6. And negative 6 plus 6 is 0. So we just showed what they gave to us there was actually true. You can trust it if they say it's given. Okay, so we proved that, we showed that. We didn't have to, but I just want to see that they weren't lying to us. The book always doesn't lie, but of course they were lying slightly by having that as a 2. I didn't make this slide, they did. I just delete things, I don't add them. So solve the polynomial equation. This set equal to 0. So if I wanted to solve that, then the problem here is we're not used to typically just factoring out something that's to the third power, unless it's like a special formula. But since I know that 2 is one of the solutions, it's one of the zeros, and I want to solve the rest of it, since I know 2 is a 0, I'm basically going to factor it out. I'm going to take it out by dividing the polynomial by a, by 2, right? A is 2 because 2 minus 2 would give me 0. Okay. So I had to know the 2 actually was a 0, so that had to be given to me. But I'm going to use that to figure out what's left out if I take out x plus 2. So let's start out. So 2 is my a value there. And then we have 3, 2, negative 19, and 6. No blank spots there. We bring down the 3. 3 times 2 is 6. 6, and remember we're adding straight down here, gives me 8. 8 times 2 is 16. And negative 19 plus 16 is negative 3. And negative 3 times 2 is negative 6. So again, we're just kind of doing this whole thing, and that gives me 0. So what I have left is going to be 1 degree less, so this is 3x squared plus 8x minus 3. In other words, here's this. I also divided it by this, right? 2 is that factor there. So this function could be rewritten, factored, as x minus 2, the factor I divided it into it, multiplied by what was left over. And it's possible I can still keep on going here. To find the other zeros, now this is a second degree polynomial, quadratic, if you will. I can see if that can be factored even further. 3x squared plus 8x minus 3. I know this is a little more complicated than some of the other factorands because we have the a value here of 3. That changes things. We have to do more of a plug and try. We just have to plug these in. I want to be confident of my signs, and I know they have to be plus minus or minus plus. They have to be opposite because my last number is negative 3. The only factors of 3, lucky for us, are 1 and 3. And so I'm going to try putting those in, 3 and 1. This gives me positive 1x and negative 9x. Adding those together gives me negative 8x. That's what I wanted here, except it's the wrong sign, which only tells me that I just need to change these symbols here. So switch the pluses and the minuses. We'll put the minus here and the plus here. And now that would be negative 1x, positive 9x. That gives me positive 8x, my middle term. So I know that this is the correct way. So if I was finding all the zeros here, we have x minus 2, 3x minus 1, and x plus 3. This is the factored version of that 3x squared plus 2x, that should be 3x cubed, plus 2x squared minus 19x plus 6. So if this was set equal to 0, I know my zeros would be 2. For this one, well, let me look at it this way. 3x minus 1, we want to know what x value will give me 0 for that. Okay, well, add 1 to both sides. We see 3x is equal to 1. Divide both sides by 3. We see x is equal to 1/3. So 1/3 is one of the other zeros, one of the other solutions of this when f of x is equal to 0. Looking at it as just kind of a shortcut way, just like here, we take the root, but we take the opposite sign. Right, because you set this equal to 0, we have to add it, so it's going to become the opposite side. Or if it's like here, it'd be subtracted, so opposite sign again. And then if there's something in front of x, we have to divide it. So opposite of this divided by whatever's in front of x, the coefficient of x, gives me positive 1/3. And then, of course, the last one is negative 3. These are the 3 roots, the 3 zeros of that. It also is giving me the broken up polynomial factors that give me the overall larger polynomial function. And that's our conclusion for this particular lesson. Thank you.